Good morning, everyone. We will continue our discussion on the clustering, which is the third major analytical task that we are learning. So we have started discussion in the previous session. We have identified the types of what is cluster analysis. We have discussed the basics associated with the cluster analysis. Then we looked at what is a good clustering, how do we define it, and we have, this is a pretty intuitive definition that is based on high intra-cluster and low inter-cluster similarity. Okay, Mr. Nagabhushanam, thank you for the wishing the happy Ugadi. Yeah, I wish all the participants a happy new year. I think it's not for everyone. I think in India about only quarter of the people observe New Year today, but happy new year for all of them. The quality of clustering depends on the similarity measure, and we want it to do everything that an intelligent and very intelligent person does it, because this is after all a machine learning, and we want to give the best algorithm for the machine so that it gives the best possible solution. We looked at two major categories of clustering. There are several ways in which you can differentiate clustering, but one way in which you can do it is partitional and hierarchical. So when we have the points, all we can say is that this group of points belong to one cluster and this group belongs to another cluster. That becomes a partition. But if we say that, let's say we have some more points, this is representing one cluster and this is representing another cluster. So now we are creating a hierarchy of clusters. So we have seen that this can be one major differentiator. So for partitional clustering, we have looked at k-means algorithm, which is a very popular clustering algorithm. Here you need to specify the number of clusters and then you go ahead with clustering, and it's a very simple algorithm. I hope I have the algorithm here. Okay, okay. The algorithm will show it. This we had seen it last class, but I'll show it. So we were looking at, after going through the algorithm, we found the challenges are finding out k good initial centroids, because this assumes that you need to find k clusters. You need to propose k initial centroids, in the sense, so you may use some mathematical techniques, you may use algorithms, you may use programs or any logic, but then you need to propose k initial centroids. That's not as easy as we would like, because we will be doing clustering in a very large data. So not something which we can easily visualize on a sheet of two-dimensional paper. So now what happens is, it's not easy for you to find out where are the real clusters. So multi-dimensional, you simply cannot visualize, and large number of clusters, and then there are no distinct clustering. That's one aspect. But as it is, even if there are clustering in large volumes, it's in large dimensionality, we don't know how to plot and visualize. So in most of the situations, we cannot find where are the real clusters. So now we want the machine to help us find the real clusters. But then the k-means algorithm works well if you can propose initial centroids well. And this is a calculation that we have seen in the previous class, if there are k clusters that we want to create, and there are really k real clusters in the data, but what is the probability that you will be getting one centroid from each of those real clusters? That probability is k factorial divided by k to the power of k, and for if k is equal to 10, the probability will come to less than 0.1%. And what it means that we are, in all probability, we are not giving the proposing initial centroids which do not belong to real clusters. And in some cases, they will adjust themselves, and because as we know, as the k-means clustering algorithm executes, the centroids will keep moving. So they may finally move to the real positions, and then we are going to get the real clusters. But sometimes they don't happen. So let's, since I was talking about the k-means algorithm, and so what I will do is I will go to the slide where we have the algorithm. This is just for the benefit of some of you who may not be present in the last class or may not remember that the partitional clustering approach of k-means. So we have a centroid for each cluster, and then each point is assigned to the cluster with the closest centroid. Okay, and then in the k-means in general, the centroids may not be real object. So this is to say, if there are three objects like this, the centroid may be represented by this point, which is not a real object, but that's pretty good because where we have all numerical coordinates, and we can represent a fictitious point which is representing the weighted mean of all the points. Okay, so it's a very simple logic. Select initial centroid, and then k clusters are formed by assigning all the points to the closest centroid, and then recompute the centroid, and then repeat. And we keep repeating it until the centroids do not change. That is to say, we have reached a kind of an optimal position. So there is nothing to reassign. All right, so now we will go back to the challenges with the k-means. Now let's look at some data to see. Here we are able to see that there are 10 natural clusters. Okay, 10 natural clusters. And we have assigned the initial centroids like this. And after the iterations, they adjusted themselves, and then after all the iterations, we are getting the real clusters. So that is to say, in this case, we have got real clusters. So this is good, and the solution is good. Now let's take another approach. So here, let us say this was the initial centroids. Okay. So what we did was that some of the centroids were assigned to multiple centroids in single, and the point, the difference between then and here is, here in each of these groups we had two centroids, and here we have only one centroid in this group, and there are some groups with this group with three centroids. Okay, now let's start If the algorithm is executed, this will be the final solution, and then even if you do the iterations, it is not going to change. So what it means that this is ending up with inoptimal solution, because there is a it has doesn't have that ability to find out a global optimum. Though the function that we want to minimize, which is the sum of the squares error, that can give us the global optimum. But then the k-means algorithm is not directly looking at that function. It is trying to go in a stepwise manner, and this will be stuck sometimes in a local optimum and will not be able to reach the global optimum. So what can we do to solve the problem of initial centroids? Multiple runs, but the probability is not favorable. Okay, and then we can also try other clustering techniques to determine the initial centroids. So use other types of clustering techniques, or we can select more than k centroids. We want k centroids, but choose initial k centroids, and then after the algorithm finishes execution and you get k clusters, you choose among them which are the most widely spread out, and then drop the rest, and then accordingly you proceed. Or you can do some pre-processing or post-processing, in this case post-processing, do the clustering, and then you think in terms of what to do next. Okay, Mr. Vivek's question is that NP hard in software terms, does it mean that there is no global optimal solution? No, 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 no. It is just that the machine is unable to find the problem within polynomial time with respect to the parameters we provide. And this is certainly not an NP hard problem, but the challenge is that we want to be able to do it in realistic time, because NP complete the problems which are P, which can be done in polynomial, and the NP problems, these are theoretically which are impossible given any machine with any effort. In general, cannot be solved. But in this case, our we are greedy because we want this is a business problem. So many times we want to cluster the products, we want to cluster the customers, we want to cluster the regions, markets, cities, land, and everything. So in that case, this is a real business problem, and then many times we have to solve many problems, such problems. So we want to solve it with real machines. We don't want to buy supercomputer to solve this type of problem. So we want an algorithm which can close very quickly, and we will see that K-means algorithm is very efficient algorithm. So it's nothing to do with the impossibility. Okay. So we look at what are the options we have is the pre-processing, which is we need to anyway do this, normalize the data and eliminate the outliers, and post-processing, then eliminate small clusters that may represent outliers. And if we see that there is a very loose cluster where the high sum of squared error is present, think in terms of splitting it, and merge clusters which are very close and they have very small sum of the squares. There are variants to this k-means, which can be based on how do we select the k-means, how do we calculate the similarity, and how do we calculate the cluster means. And we can also have, when we have a categorical data, we can have k-modes algorithm. K-modes is that when you have a categorical data, for example, we are saying there is an object, the object variables are, one is gender, profession, and then city. So we have all categorical variables. So in such case, k-means will require the calculation of mean. So there is no concept of mean. So we have to go with the modes. Okay. So this is a variant of which is based on a similar logic, but this can be far more complex to execute because there is in previous case the mean computation used to make our the problem our algorithm more tractable. So the thing is that we need to keep on updating the modes. Uh, so that can be one. Uh, okay, I'll answer your question in a minute, Mr. Nagarajan. So k-means has a problem when the clusters are of various varying sizes, densities, and non-globular shapes. So we can see that there are different sizes data. So these are the natural clusters. Okay, these are real clusters, and these are the clusters created by KV. So we can see that this has broken the real clusters arbitrarily because they are of different sizes. So some of the squared error, so essentially the mean calculation and all that. And there is also the problem is that there is no clear gap between the clusters. Though we can make out by visual inspection in this case because this is two-dimensional data, but we don't get the benefit of visual inspection for higher dimensional data. And the k-mean suffers when there is a widely varying density for the data. We can see that these are the original points and these are the real clusters. These are the real three clusters. These are three real clusters, and it has divided into, these are the k-means. This is real. Okay, so that can be one problem. And then it has a challenge with the non-globular shapes because again this is we are visualizing because it's two dimensional because it is depending on the distance function. So we can see that distance between these 2 points is much lower than the distance between these 2 points. So if you look at the distance between these two and then the distance between these two, we can see that though we can see that these are the real clusters of arbitrary shape. So what this is going to do is that it is going to create clusters of this kind. Okay, now let me just answer Mr. Nagakrishnan. Not most of the time to solve the kind of problems we use software for exam only theory or how. Okay, Mr. Nagabhushanam, you have asked a good question. And I think I did answer this once. You are saying that we can solve the problem using software, so why is it that in exam we have to calculate? Am I right? Is that your question? Maybe I'll unmute you. Mr. Nagabhushanam, you're unmuted. Can you speak? Okay, I'm not hearing from him. Uh, okay, you're not able to speak. See, the point is like this. The software can solve many problems. For example, if you are a CEO and let's say you are the CEO of Maruti and you need to analyze the sales and slice, dice, roll up, drill down. You want to find out the reasons for the profitability, which is is it a service issue, customer issue, or is it the salesperson issue? Why we are not selling and why we are not selling in well in south region when we are selling so well in eastern region and so on. So if you are a CEO, you have to get the answers. So you will be getting the answers with the help of software, right? But you do not know how to do the programming and you can still get all the answers very accurately, right? The challenge is that our focus through these courses is that you understand how the solutions come. So for that you need to do some computations with hand, right? Otherwise, how will you know if you are saying that probably I will not ask the CEO of a company to come and attend this class to learn about how to analyze the sales data because but then I am sure I hope I am assuming that none of you are in that position where so you have to solve the problem, so you need to know what is the how the problems are getting solved, right? So many times you can get not one but 100 products available in the market. You to evaluate the products, you need to know something, right? Okay, Mr. Vivek has another question. Suboptimal solution can be due to initial selection of centroids. All right, and then if we ensure there is a maximum distance between the now the question is this: K-means algorithm itself does not calculate the distance between all the points. Let's look at it this way. So K-means to calculate distance between any 2 points. If I have n points, okay, I want to that n can be 1 million. I hope you won't object to that because there are so many large organizations dealing with so many large data objects, data sets. So now, if I want to calculate distance between every 2 points so that I will take the maximum distance, now I need to calculate the NC2, which is of the order of n square. Okay. Now it is no longer a linear solution; it is non-linear. So that means it's actually far more. It will take the calculation of this distances will take far more time than executing the k-means algorithm, which is a linear algorithm. So now the first thing is that you need to do that, and which k-means algorithm is not doing. I hope have I answered your question, or you still think that Mr. Vivek? Okay, fine. So so what happens if you choose too many centroids at the beginning? So now what we do is that this previously we attempted it as a two means problem. K we have taken as 2, okay, and then instead of k taken as 2, let's take k is equal to 10, and we create this. And after that it is done, somehow we can recognize that this is one natural cluster and this is another. Then we can solve. But then this works when data is highly visualizable. But visualization itself is a very big problem. We cannot visualize a high dimensional data. And same thing can happen even with respect to the density. Varying density, we choose too many clusters, and then we are able to get the natural clusters. So here there are three clusters instead of, and then we knew that there are three. So we started with the 3 initial centroids. We didn't get good value, but then we started with 10 initial centroids. We got a better response. Same thing with the arbitrarily shape. So now to look at some of the challenges with k-means. The best thing about it is that it is a very efficient algorithm. It is linear with respect to the number of objects, number of clusters, and number of iterations. So that is the order of TKN. Okay, so that's pretty good. That's pretty good. Considering that if see when we are solving with 10 objects, 100 objects, and we have got a powerful machine, it doesn't matter. But when we are dealing with 1 million objects, a linear and non-linear solutions will make a big difference. So order of n and order of n squared means a lot. In this case, you may get with a million points. You can start the algorithm and you will get the answer within a couple of hours. Here you may have to wait for a week. So that's a significant difference because you need to iterate many times to get a good solution. And it terminates at a local optimum because that is how the k-means is defined. So we can't do much about it. And it works only for which we can calculate a mean. Mean means it has to be a continuous variable, so for which we otherwise we can only calculate mode. Okay, and for categorical data we end up with k modes. K modes will not be k modes can work for categorical data, but its efficiency will not be linear. And we need to specify the number of clusters in advance. And it is sensitive to noise, outliers, and it's not good with the non-convex sheets. So there is a alternate which is a k-medoid clustering. So k-medoid clustering works not only for objects which has only continuous variable. A combination of continuous and categorical can also it works. The reason is that here we do not depend on mean, but we depend on medoid, which is a real object. Real object. This is essentially a imaginary object. The object does not exist, but we have extrapolated it because but through mean computation we got a new point which is at the center equal distance, and then we have considered that as an object and we computed. But medoid deals always with the real objects. So you start with a set of medoids and iteratively replace one medoid by another, a non-medoid, and then we calculate somehow the distance. And then, but then it doesn't scale well. It is not linear. Okay. So there are some sophisticated algorithms which try to improve upon a medoid. Okay, Mr. Nagabhushan, medoid is an object which is representing the cluster. It is not mean of the cluster. Have I answered your question? A mean of the cluster each can be a real point or an imaginary point. It is, yeah, medoid has to be part of the cluster. A mean need not be a part of the cluster because mean is an imaginary point. Okay, fine. All right. So now we will proceed to further. We start. Okay, Mr. Vivek is asking, then how do we calculate medoid? It's far more complex because we need to consider categorical continuous values, and then we need to keep comparing each possible candidate as the best medoid for the cluster. So it's not easy. It involves a significant computation. That is why it is not linear. Mr. Vivek, have I answered your question? We have seen how to calculate the distances for so many types of values, binary, categorical, and ordinal. And so we used to use multiple criteria and then select each candidate and then do that. Okay, so this does with the partitional. Let's go into hierarchical methods. What we do is we take a couple of minutes of break. We already spent almost half an hour.